Welcome back to Chemist Corner. Today, we will be working with acids and bases. However, acid-base reactions are painfully boring to watch. Clear colorless solutions mixing with clear colorless solutions to result in, you guessed it, clear colorless solutions. So to make it more interesting, I added a little universal indicator. That's what you're looking at right now. The different colors universal indicator shows when mixed with various pHs. However, a universal indicator is not a single compound, but rather a mixture of several common acid-base indicators. Thymol blue, methyl red, bromethymol blue, also known as bromothymol blue, and lastly, phenolphthalein. Because the indicators that make up universal indicator have different transition colors at different pHs, this allows the mixture to progress through a variety of colors depending on the pH level of the solution being measured. Thymol blue makes its first transition from red to yellow at 1.2 to 2.8 pH range. Methyl red goes from red to yellow from 4.8 to 6.0. Bromethymol blue goes from yellow to blue through the neutral zone, and thymol blue has its second transition from yellow to blue from 8.0 to 9.6. Lastly, phenolphthalein starts out colorless, but through the 8.2 to 10 pH range turns magenta. Well, that's in theory. What kind of red? What kind of blue? So I tried it. I tried my universal indicator with some solutions with approximate pHs, and this is what happened. Based on the indicators that make up universal indicator, the expected colors for universal indicator would be as follows. If the pH is less than 3, we should only see red. If the pH is between 3 and 6, we should see a progression from red to yellow. In other words, we should see orange. Around the neutral range, it should be a blend of yellow and blue, making green. Anything above 8, we should see blue, but once it gets past the phenolphthalein endpoint, anything above 9, we should see a blend of the magenta with the blue in order to see purple. In practice, this is what we actually see. In this video, I will be reacting hydrochloric acid with the strong base sodium hydroxide to produce the neutral salt sodium chloride and liquid water. When the number of moles of HCl exceeds the sodium hydroxide, then we should see the red-orange acidic colors in the universal indicator. As long as the sodium hydroxide is in excess, we should see the basic colors of the universal indicator, the blues and the purples. Right now what I have in my Erlenmeyer flask is simply 250 milliliters of distilled water. And I'm going to add a little bit of universal indicator, which will allow me to determine what the pH is. And you can see from the color, it's pretty neutral. Green tells me it's very close to being neutral. I'm now going to add just a couple of drops of dilute sodium hydroxide. This is 0.1 molar sodium hydroxide. And with one drop, you can already see it turns bluey purple. 2 drops, it gets darker blue. 3 drops. 4, and I think I got a 5th one in there, and it's now fully purple. That tells me it's strongly basic. Sodium hydroxide is a strong base. In my burette, I have the same concentration, 0.1 molar, of hydrochloric acid. And I'm going to add just a couple of drops of hydrochloric acid. Watch where the drops hit the solution. Okay, that was 2 drops already, and you can see the purple color has gone away, the blue color is back as it mixes, and it's looking a little bluey green. Add 1 more drop, and the acid is neutralizing the base. We're back to the green color that we had at the beginning. Neutral water. Add 1 more drop. And the green color goes away, and we went right through the yellow and we're into orange already. This is telling me it's weakly acidic. I'm going to add a couple more drops here. There's 1 more drop, and you can see there's a red color coming, and just want a last drop there, and now we're fully red. This shows you how rapid an acid-base reaction can be. As soon as the drop hits, the color changes. My universal indicator tells me when it's purple, it's strongly basic. When it's red, it's strongly acidic. This kind of reaction, a reaction between an acid and a base, is called a neutralization reaction. When both the acid and the base are strong and equimolar, then the product salt does not hydrolyze, resulting in a neutral solution. In the previous example, this neutral salt was sodium chloride. As before, I have around 200 milliliters of distilled water in an Erlenmeyer flask. I'm going to add some universal indicator again to show, yes, it is neutral. It is a greeny yellow color telling me neutral. Last time I added a strong base of sodium hydroxide. This time I'm just going to add a few crystals of a weak base, sodium carbonate. The sodium carbonate dissolves very rapidly, and as you can see, it turns purple. It is very, very basic. It's a weak base, but it's basic. Now I'm going to add my 0.1 molar hydrochloric acid, again, 1 drop at a time. And watch where it hits. As the drops hit the solution, the HCl is neutralizing the carbonate ions. Let's just stop it right there. And you can see it's gone from purple to blue. Add 1 more drop. And as it mixes in, it dissolves that HCl. 2 more drops. 1 more. And you can see the hydrochloric acid is neutralizing the weak base. We're back to green. 1 more drop. We're in yellow. 1 more drop. And you can see us going through the rainbow colors of that universal indicator. 1 more drop and we've just about got rid of the green color. 2 more drops and we're in yellow. And again, the hydrochloric acid is neutralizing the sodium carbonate, the weak base. 2 more drops takes us to the end of the yellow color. 2 more and we're getting into orange. Oh, not quite, still yellow. And as the acid is added, you can see it becoming more and more acidic, going from yellow through orange and now going into the red color. You notice it's taking a lot more acid to neutralize my weak base than it took to neutralize my strong base. If we stop it here, we're going to be pretty close to done, but not quite. It's still just orange. It's not fully red yet. 4 more drops, and we're kind of cherry pink. And now we're into the red. The difference here is not the strength of the base. The difference here is the amount of the base. I only put in 2 drops of the sodium hydroxide in the first example. Here I put in, well, it didn't look like much, but the carbonate had enough concentration that it took many times more volume of the acid to complete the neutralization. That is acid-base neutralization. In my second neutralization reaction, I reacted the strong acid, HCl, with the dibasic weak base, sodium carbonate. The initial products were sodium chloride and carbonic acid. However, the carbonic acid rapidly decomposes into gaseous carbon dioxide and liquid water. If you enjoyed this video on acids, bases, and universal indicator, please like, comment below, subscribe, and tell all your friends. See you again on Chemist's Corner.